Bay. Awesome. So if you guys will give me a second, I'll go ahead and if it'll let me, we'll share the screen. I've got another one down here. I'd like to take a minute, first of all, to thank everybody that got it. Thank everybody that showed up and spent a little bit of time. We'll run this a little bit differently. I haven't thought that a lunch and learn was a great opportunity for us to maybe not do most of the education part, but start that exchange of ideas to get up to speed on certain topics and maybe even think about where the industry is going. And what I'm going to present for you guys today has a lot to do with where we're going. It's called hybrid EV and evolution. So my thought was to present just some material about where the industry is going and what we see is definite trends. And I will tell you from my company's perspective, we have decided to go all in on this evolving technology. So we will be stocking and do stock now plenty of parts for these EVs because we're going to realize there's a lot of opportunity for us to work on these vehicles for regular car problems, not as much the EV side. We're still going to have suspension and tires and brakes. We still have coolant loops, and there's many more of them now. We still have the creature comforts that'll have to be fixed, your heated seats, your air conditioning, and all of these systems become more and more important because they're integrated to how the electronics and the batteries are cooled and serviced also. So the idea today is we're going to run fast and loose, and I just wanted you to know that from the company's perspective, we are all in to make sure that the evolving and emerging technologies are supported from our supply side. And then I'm going to add what my specialty is, and not only as an instructor, but try to tell you my perspective and what I've seen from a technician in the field as I work on and see this stuff. A little bit more background of me. A lot of you guys live out in the West Coast where we see a larger percentage of adoption of those EV vehicles. Myself, I live in Cleveland, Ohio, and while Cleveland is not a hotbed of EVs, right down the road from me, the city of Columbus, Ohio, has embraced this technology wholeheartedly. So I've been privileged to take classes from Nissan on their Leaf and from Ford on all their propulsion. So what I bring to you is not only from a perspective of getting trained, but actually having the pretty experience of these vehicles and everything else that we see in our industry, most of, if not all of the time. So things that we're going to cover today, I'll go a little bit over safety because we really can't talk about the high voltage we have on vehicles without making sure that we're safe. We'll talk about the evolution and the constantly evolving world of electric vehicles, whether it's the chemistry of the battery, the way the motors are constructed, the efficiency of each part of the vehicle. It has all evolved for a long, long time and continues to do it on a daily basis. In fact, at the end of this presentation, it will absolutely be obsolete because some manufacturers, some battery chemistry, some way of doing something that I describe is obviously going to evolve in the time that we're doing this. That's how fast-paced this is right now. We really wouldn't be able to talk about electric cars without mentioning the folks over at Tesla because they've really driven a lot of the innovation and have basically embarrassed other manufacturers into stepping up to the plate and start looking at things that they do. I'm a real big fan of the company Tesla and the fact that they never stop trying to make improvements on the systems they put inside of their vehicles. And I'm a big fan of anybody that takes that, that part of the business that seriously. We'll talk a little bit about diagnosis and testing to make sure that we're sort of up to speed on some of the different tools and techniques that we may need to employ when we work on these high voltage systems. And we'll talk towards the end about how important the battery management is and basically how important battery cooling is going to be for our vehicles as we go forward. So we always have to talk about safety, as I said before, and the little man with the snorkel on. And it's just not that drastic, guys. We just have to be smart when we work on a high voltage system. The reality is when the auto manufacturers first came over to the high voltage world, we really didn't understand a lot about it. So a lot of the safety, the tooling, the criteria, and the testing came right from other high voltage industries, high voltage industrial motors, elevators, things like that had already practiced this type of service work out in the field before. So one of the things that we mentioned early up is your electrical equipment has to change. In fact, I would tell you that I have a dedicated hybrid meter for a couple different reasons. Number one, my electric meter, my DVOM needs to be a Cat 3 or better meter, and it has to have Cat 3 or better leads on it. Along with that, I really don't want to have a set of leads that have been slammed in a hood or dragged around the shop, or maybe have gas, grease, and oil on the outside of them, because those products can be conductive. And if we're working on a high voltage system, I really want to use a nice clean meter that's able to be dedicated just to hybrid. So I'm not a real big proponent of telling you guys to rush out and buy tools all the time. If a tool doesn't make me money, I don't know why I would buy it. But I do understand that the difference in the meters and using my everyday meter for, we'll call it regular automotive, and saving my hybrid meter for hybrid testing and then putting it back away to keep it nice, safe, and clean and in good condition has really served me well. And I just want to point that out to you guys. When it comes to safety, I have a little checklist that I go through in my mind, and this is more about just establishing good work ethics in a good work area. If you're going to work on a hybrid vehicle in a congested shop, it's probably not the best place to do it. So if you don't have a place in your shop where you can open up 4 doors on a vehicle and still walk around it, where you can't walk around the front without tripping over some sort of piece of equipment that's stored there, that's not a really good environment to work on a hybrid vehicle. So we need to establish a safe work area. And a lot of the manufacturers will tell you what type of environment you should have this vehicle in, whether you should put cones around it or whatever the case may be. Now, a little personal note, I got to tell you, if you ever want a whole bunch of people to gather around a car, put some cones around it and tell them not to go anywhere near it. There's something about putting up warning cones around the vehicle that just makes everybody in the shop want to show up. So while I do want to follow all the manufacturer's recommendations to work safe, I also want to understand the environment in my shop and make sure that everyone around me understands when we're working with high voltage, there is an inherent danger. So we just have to be a little bit more alert and a little more safety conscious when we're working around it. As far as personal protection equipment, the big one we're going to talk about, the slide or so, are going to be the high voltage gloves or lineman gloves to make sure that we're insulated from any kind of high voltage leakage or any kind of high voltage problem until we, the technician, have disabled that high voltage system per manufacturer's recommendation, and now it's safe to work on. Anytime that we're working on the high voltage system, we're going to pull out our service disconnect. And we'll learn a little bit later that service disconnect is there basically to split the battery in half and render the high voltage system as a broken circuit. So I cannot put any high voltage out onto the system. Now, we always want to do safety testing to make sure that some sort of failure hasn't happened that would allow that high voltage to go out. But by and large, by removing that service disconnect, you've basically split the battery into two halves, therefore removing the ability for that circuit to be whole and not allowing that high voltage to come out. Inside of all of these systems, they use something called a capacitor. Now, it's not a noise filter, it's actually a voltage smoother is what they use it for. So as we start to charge up our high voltage system, we actually fill up our capacitors to about the voltage that the battery is supposed to run at. And we use those capacitors to allow for voltage fluctuations and to cover them up as we're synthesizing AC voltage through our inverter to make the AC motors that drive the car actually work. Remember, we have to do a lot of inversion and conversion of electricity on these vehicles, from a DC to DC converter going to help and dropping it down to 14 volts to charge up our service battery, the whole way up to allowing 270, 300, whatever the voltage of the battery pack may be, allowing to pass through it so we can charge it up. Those capacitors allow us to smooth everything out as we drive the vehicle. And it also has an ability to store at least a little bit of energy. If we had a catastrophic high voltage failure, that we would still have at least a little bit of energy to slow and stop the vehicle down at that point. Anytime that we're going to work on a high voltage system, it's our job as a technician to verify that high voltage system is as close to 0 volts as possible. And that'll be per the manufacturer's recommendation. We're just going over the safety stuff in the beginning to make sure that we all understand while there are some inherent risks to working on high voltage systems, if we practice the safety and the techniques and the ways that we're supposed to work on it from the manufacturers, you'll find that they're not hard to work on. They're not dangerous to work on. They're just our precautions we have to take before we jump in and start servicing them. The gloves that I spoke of earlier usually come in at least a 2-pack or a 3-pack, meaning there will be 3 sets or 2 sets of gloves in the bag that you get. The ones that I order usually have a nylon that will go, or a small cotton glove that will go on the inside to stop your hands from sweating. Then we'll place the large rubber gloves that should be pretty well fitting to your fingers, because you will need to have a little bit of dexterity to do some of the work we're going to do with these gloves on. The last piece, and probably the most important piece, are going to be the leather overs, the leather over gloves that go on top of the rubber. Now, I don't want to beat safety to death here, but this is very important because we want to make sure that you never become the ground point or the current path for any of the systems that we're testing. So these high voltage gloves came right out of the lineman industry, the high voltage industry, and they've come over to our side. The outer leather gloves are protect us from puncturing those inner rubbers to allow any kind of electrical current to go through there. These gloves are certified as on a tab on them that has a date, and the gloves are only good for 6 months after you open those gloves in the shop environment. So in order to keep them very, very nice, number one, this becomes a shop supply that has to be billable, because it now becomes a commodity that you will go through. The second thing I will tell you, you have to have multiple pairs of gloves in your shop, because every once in a while you will need to have an assistant who may need PPP or PPE also in order to assist you in some of your voltage or high voltage testing that we may have to do on some broken vehicles. So there's a part number that's available for them. There's plenty of manufacturers that sell these gloves. We can even send these gloves out to have them recertified. In the past, I have found that it's probably about half the cost of replacing the gloves to send them out and have recertified. So I've taken it upon myself to pass the savings on to the customer and just replace the gloves with a new pair every time that I use one. And then I have a pair that lasts for approximately 6 months. We always want to test the gloves by squeezing a little bit of air into them, rolling them up and looking for leaks before we use them. But just remember, we do not have to spend our entire diagnostic time with these gloves on. They're only going to be worn while I power down the high voltage system and then verify through my meter that I have the high voltage system has been taken down and there's no residual voltage that could be harmful. Once that test has been established, I'm going to take these gloves, put them right back in their safety bag, and put them in the bottom drawer of the toolbox until I have to power the high voltage system up. So don't think that we're going to be trying to screw in 10mm bolts with these 2 or 3 pairs of gloves on your fingers. We only need these to make sure we're safe during the power down process. Now, speaking of our high voltage safety service disconnect, this is something that I still think is funny in my lifetime, that we can standardize so many things on a vehicle, but this switch just seems to never have been standardized. While it usually will split the battery directly in half into two small sub packs, a lot of the times the switch doesn't look the same from make to make or model to model. We can go back to some early Hondas that literally had a switch that looked like a service breaker out of the fuse box in your house. The left hand and bottom center are both out of Priuses, and while they look similar, they did point different directions and have a little bit different tab that you had to release in order to get them out. As long as we're talking about that, if you guys have ever struggled to unplug a PCM connector with the super secret combination of push this tab and pull this lever and move this cam over, these are almost always going to have at least a second position for safety to unlock. So I'll show you one in a Ford a little bit later that you have to release the handle halfway and then pull a collar up, and then you can release the handle the rest of the way. I would tell anybody, if you're taking one of these out, please take the time to look up the proper information to how you're supposed to get this interlock out without breaking it. Because once we break the plastic, once we break a tab off, it's really not doing the safety job that it was supposed to do. If I look at the interlock connector, and this one's out of a small Toyota, you'll see that there's two large high voltage battery contacts. In a lot of cases, there's going to be a fuse that lives in the end of this connector also, a very large 600, 1100, 1200 amp fuse that can live there on some models. The two that I want to point out also in the picture, in the bottom center of that connector, you'll see there's two tiny little tabs. And those tiny little tabs are there for a service interlock 12-volt loop connection that helps us understand if we have all of the high voltage connectors still intact on the system.
Bill, could I ask a question, please?
Yes.
Should we be looking at a slide, or is that coming later?
I thought you were looking at slides. I'm sharing a
No.
screen. Did it not come up, dear?
It didn't, no.
All right, let's try it again. Screen number 2.
There
It
we go.
says-
Now we can see it.
All right. I'm so sorry, folks. I thought you had saw that. In fact, let me back up one slide so you saw what I was talking about.
Oh,
And
that'd
then
be
we'll go
great.
forward with it. Oh, no problem. I'm sorry. So I was mentioning those service connectors. In fact, we'll go back to the gloves. Here's a picture of the gloves. If you guys haven't seen them before, it's simply a big, thick rubber glove, and they're insulated to the level that they will protect us from a lot of voltage. These were used in the high voltage industry, and it's something that we should have available at our shop at all times if we're going to work on high voltage systems. So there's the Napa part number. These are the ones from OTC. We put it in there not to sell you guys gloves, but just because I don't want to get 100 phone calls about what that part number was that I did show. So I wanted to make sure that was in there, and we'll make sure that Brenda gets a copy of them if you guys want to look for them. As I said before, these gloves do need to be taken care of. They're only good for 6 months after we open them. And you can see this is an older set of gloves that I had. I usually take these around for demonstrations so everybody can get, an idea of how thick and how big and bulky they are. Here's a shot of all those service connectors. I had that little complaint about them never standardizing these. So the bottom right-hand corner, that was a twist lock connector out of some early Ford products for their Mariner and Escape hybrids. The other cam lock ones you can see are very similar between most of our Toyota units. The big green one up on the top, that's just basically a battery kill switch like you would see on a high performance car. And one of the complaints I have, and I try to take it to everybody to listen on behalf of the industry, is if we can standardize everything else in the industry, how can we not get to the point where we standardize this plug to make sure that it's going to be the same removal procedure each and every time? Back to the picture where I should have had it up for you guys. As you can see, these high voltage contacts are basically the two big blades that are going to connect in the right-hand picture, the two sides of my lithium ion battery. Once I remove that service disconnect, even though that the high voltage wires could still be connected on the other end of the battery, we really don't have a circuit going through the battery at this point. That way, we would be able to make sure that we're safe when we're working on the high voltage system. The two little connectors on the bottom of it are the two that are going to be removed first. And those two little connectors actually feed into this thing called an interlock loop. What all these EV manufacturers have done is run a discrete about 12 volts, maybe 200 milliamps behind it through each one of these connectors. And each one of these connectors has a different resistor in it. So very quickly, by monitoring this loop, the PCM or the battery control module, whoever's in charge of this loop, has the ability to see if any one of these connectors is disturbed or open at that time. And the minute that any time that 12-volt loop opens, we will completely open up all the contactors inside the battery, therefore rendering the battery pack inert, or the battery energy still in the battery, but not able to go out to the car. This is the biggest reason why we instruct first responders to kill the 12-volt battery anytime they approach these vehicles. Because once I lose the 12-volt battery, I've lost the ability to close the contactors, and we've lost the ability to supply the 12 volts to this loop, therefore opening up the contactors by default. So these are super safe, and there's a loop of safety that's around them to tell if the connectors are still connected. It allows us that even if you tried to disconnect this while the system was live, the minute that 12-volt loop gets broken, the high voltage system shuts down, and therefore there can be no arc flash from plugging a 200 or 270 volt system. If I look a little bit farther down into the electronics of it, these are the capacitors I talked about before. They're used to hold and store those voltage and make sure that we don't have any kind of high voltage disruption when we accelerate very, very harshly on these vehicles and dump a lot of energy through the motor generators. Before service, these capacitors have to allow time to bleed down, because they actually get up to a very high voltage, and this can go ahead and remain in the system for up to 15 minutes on these Gen 1s. In later years, most of them gotten down to about a 5-minute spec for that energy to be dissipated, because now they're actually pushing it through the motor generator, and it's a lot easier to dissipate that energy after we shut the vehicle down. This is why we tell people not to work on any hybrid systems or any electrical systems until we've given us enough time for these capacitors to bleed that energy down. Some of the other safety features that we see all over our hybrids, if we look in the picture now, you'll see there's a lot of steel webbing that go around all of the high voltage cables. And that's there for a couple different reasons. A lot of people will think that's some sort of shielding to get rid of RFI or any kind of magnetic interference. And while it may serve that purpose, by and large, that's not really what it's there for. If you look really closely, that steel webbing actually grounds to the outside of that inverter case. And what this is there for is, number one, if there's ever a catastrophic failure, we will have an immediate short to ground against that metal cable, and that will stop all hybrid energy or all electrical energy from being passed out of that battery pack. That'll open up those contactors for us. So it's purposely going to cause a short to make sure that we kill the high voltage system. The second thing that it does is, because it's such a fine mesh and it's such a stout piece of wire, it arrests the cable in an accident, so it cannot flop around. And once it grounds itself out, it's in its safety net, and it cannot be flopping around and touching other pieces. So in the event of a catastrophic failure or a cable that gets severed, it is automatically there to, number one, arrest the cable, and number two, provide a ground pass so we open up those contactors. So the safety aspect of these things is just incredible. They are safe to work on if we use our heads and follow the manufacturer's recommendation. Now, along with the check engine light and the wrench light, we actually have another light that's been added on to hybrids, and it's actually an international symbol or a master warning for the high voltage system. Now, we all know that our wrench light means we have some service work to do on the vehicle, but it may not necessarily be related to emissions faults. We all know that the check engine light is related to an emissions finding fault. But the misnomer out here about this triangle is everybody thinks this has to do with a high voltage failure. And in reality, that's not exactly what it means. It's a master warning system that lets you know the PCM, the computer system of the vehicle, has taken it upon itself to shut the high voltage system down. This could be because of a high voltage problem. In some cases, it's not a high voltage problem. The Prius that you see in the picture in front of me, it's a local shop around here, and you can see on top of it the back seat and part of the battery, and everything's already apart on this vehicle because of this exact orange warning light. Well, when we got there to look at the vehicle, and you'll notice there's a mass airflow sensor picture on the right-hand side, the only problem with this vehicle was a spider web. It got sucked down inside of that mass airflow sensor. And I'm going to turn it into a case study, but here's how these two correlated. In order for a hybrid or an electric vehicle to allow you to have high voltage, there's certain things it has to understand about that engine. And in this case, it had to understand that the engine had started. Well, it could see the crank sensor, but when we looked at the mass airflow sensor, and this poor little 1.5 liter engine was pulling over 4 grams a second at 1200 RPMs, the PCM looked at the math and says, well, that doesn't make any sense. That engine cannot move that much air. Now I don't even understand if the engine's running correctly. So his programming told him, turn on the high voltage battery light, take the high voltage away, and don't let the hybrid system work, because I don't understand if the engine's working correctly. So I want everybody to understand, just because you get that orange triangle on it doesn't necessarily mean that it's going to be a problem with the high voltage system. In this case, it was an engine system that created a problem with the high voltage, not understanding the engine was running, and therefore it was disabled. On the other hand, we could have something as simple as these old prismatic cells from Toyota that leaked a little bit of electrolyte out. Now, electrolyte is conductive to electricity. So you can see in the picture, by the time this cell had vented enough, we created a path for high voltage to find itself the whole way down to the ground of the chassis. Now, there's no way we're going to send 1,000 volts through that electrolyte, but all we have to do is create enough of a path that the resistance is lower than the manufacturer's specification, and then we will immediately open up the contactors and make sure that the high voltage battery cannot send any kind of energy out to the system. This could happen for many different reasons. So I've showed you the one with the mass airflow sensor, had nothing to do with high voltage. This one actually is a high voltage leak because of electrolyte that has come out of it. And I've seen something as silly as condensation inside of the transaxle, creating a path through the motor generators to the case because of too much water in the transaxle. This was a simple service. We didn't have to replace the transaxle. It was just from condensation from sitting in a hot, cold, hot, cold, hot, cold environment. This was a simple change of transmission fluid, and that vehicle served for many, many miles afterwards. So I just want everybody to understand, just because you get that high voltage battery triangle, it doesn't necessarily mean it's end of life for the battery, nor does it mean that you're definitely dealing with a high voltage problem. If we're ever looking for battery isolation faults, one of the things that we do on the early Toyotas was we would disassemble the top of the battery pack, and we would use our service main relays, those contactors I spoke of, to do the testing on one half of the battery at one time. So I would go from the contactor the whole way back to the service disconnect, and that would allow me to test the resistance to ground or to another side of the pack on one whole end of the battery pack inside of the vehicle very, very quickly. So we would hook up the negative lead just to a chassis ground, and then we would take the positive side right to the battery terminal side of those service main relays, and it would allow us to check for resistance over to the chassis ground. And if we had corrosion, or that corrosion track that I showed you, it could cause a low enough resistance spec to actually serve or to have this problem. Now, I will tell you that this is probably going to be your beginning of working on these, because I try to tell every technician out there, the chances of you working on a brand new Tesla or a brand new Hummer or a brand new F-150 Lightning, it's not the way the world works. We're going to work on our third-hand Prius. We're going to work on the car that was passed down. That's how we're going to get into this high voltage system. We're going to work on cars that are broken, not brand new cars. So I like to bring this out to everybody so they understand it's going to be baby steps. I've worked on hybrids for years, and to tell you the truth, I've probably done maybe 25 or 30 high voltage system problems on the vehicle. Usually it's going to be a brake issue. It's going to be a cooling fan issue. It's going to be a coolant issue. What I'm trying to say is I fix a lot of car problems on hybrids. I don't fix a lot of hybrid problems or electrical problems on these vehicles. They are out there to fix, but it doesn't seem to be the bulk of my work. So when I go over the safety part and I end it, I just want to do a synopsis to make sure that it's only safe for us to work on these high voltage systems after we've opened up that service disconnect and split the battery, given enough time for those capacitors to bleed down, and then we've used our hybrid safe meter to confirm that we have low voltage in that high voltage system. It's not up to us to assume any of this. We really cannot be lazy here. We can make no assumptions. These are tests that are going to make it safe for you to work on the vehicle. Once you've confirmed it, then it's safe to continue working without your high voltage gloves. You're just working on a car at this point. We wanted to put this part up front so everybody understood that even though that the world is changing for us and the propulsion of our vehicles is going to change, the being smart, looking up service information, having the correct tools, that part of our job is going to continue to evolve each and every day. I don't know how many of you guys get to see these, but I do have a local museum that still has one of these that we can get to and actually see. Most of these were bought back. This is the EV1 from General Motors. It's the only one that I know of east of the Mississippi that I've seen that's still intact. Most of these were taken back. And I wanted to put this in there because I've often thought it's important to understand how we got to where we are now. Now, an EV1, the thing didn't have a lot of range on it. There was an entry-level EV car, if I ever saw one. It was good work, but we were limited by the times. And if we think about all the evolution that's happened over electric and hybrid cars, the introduction of these cars has not been the best, most desirable vehicle that's ever been built. When we came out with the EV1, it was a nice car, it was a cool car, but everybody did not want this car and it was not going to be practical. We'll look at a Ford Focus Electric a little bit later. While it was a cool car and it was the electrification of an existing platform, the practicality of that car was not as high as it should have been for everybody to be able to use it and adopt it. So as we go forward and think about what's affecting or influencing the EV adoption, we're going to leave all the political and money spending part out of it. Let's just talk about the reality to our customers. A lot of people will complain that high voltage batteries are expensive, but I would counter that if you've put a transmission, a motor, or a major service item on any vehicle lately, all vehicles are expensive to fix. We've got transmissions out there that's $6,000 on Chevy pickup trucks at this point. So there are expenses out there, and most of these batteries are designed to last well into that 10 to 12 year mark. So modern ICE vehicles are also expensive. So that's become sort of a push at this point. We finally have a state that signed legislation that says we are not going to sell internal combustion engines anymore. And we have about 14 other states that have laws, trigger laws, and all kinds of other things that there is going to be a lot weighed out in the next couple of years about who's going to follow along with this. The fact that the government and the state of California have both moved to go towards this means that it's getting real for all of us. So just be advised, it's going to happen. Now, the more consumer-friendly part, I really like this because now we're getting some cool electric vehicles, whether it's a plug-in hybrid or a full EV. We are now getting to the point where we have a product where the public wants to buy it. Whether we can all afford it, that's a whole different thing, but there are products out there that we're going to be able to buy. Range is getting to the point where that 280, 300 mile, that seems to be about the target they're looking for. And we actually have vehicles out there that have over 400 miles of range in the correct environment. So we've gone a long way there. Charging and infrastructure is about to grow by leaps and bounds. If you look today, it's depressing. 50% of them don't work. We have problems trying to monetize them. We have a lot of false information out there about how long it takes to charge a car based upon what type of electricity we're pushing to it. But we are getting better. We see that General Motors is going to hook up with Pilot. We're going to put them in truck stops. All the Ford dealers are going to get them if they sell EVs. The Nissan dealers are having them. And then we've got plenty of municipalities that are spending money to put EV infrastructure together. The city that I go to down in Columbus, there are charging infrastructure everywhere around that area because they've embraced that technology. This is something I still find funny to this day. I usually ask you in class without going ahead and putting a picture up, but people don't realize this is the best-selling plug-in hybrid electric vehicle in America right now for 2022. I mean, everybody wants to go right to the Toyota, right to the Prius, and honestly, you add up all the Toyotas and this still outsells them. And what that tells me is if you build a product, this thing only gets 29 miles on electric. However, it's very innovative. When you drive it, it shifts like a regular vehicle. It's got a traditional transmission in it. It doesn't use a power split device like a front wheel drive hybrid does. This vehicle shifts and it feels like it's driving and you hear nothing because it's all electric. It's one of the most impressive electric plug-in vehicles I've ever driven. And it is the best seller out there, to the point where now Jeep is actually making this available in the Willys trim, which drops it down to about a $48,000 entry purchase, which is a lot of money, but still, to get a plug-in hybrid and sell that many of them, that really impresses me. The charging thing I mentioned before, we have got to understand what makes a battery last. There's a lot of technology that goes into batteries. And one of the things that they're really working on now is trying to balance those cells out. Is anytime that I get a cell that has a little bit more resistance in it than another cell does, that means it's going to create more heat. And that more heat is going to create a problem for the other cells and change their internal resistance around them at the same time, because that's what heat does to resistance. Well, all of these problems start to snowball, and it's really hard to get a battery pack, let alone individual cells, to balance themselves out. So over time, they've developed better ways to keep these batteries balanced. And along with that, we've discovered a lot about how we should charge them. We're looking at a Nissan Leaf, and the Nissan Leaf came to America with what they called, on the left-hand side, a CHAdeMO connector. And that was developed by Japanese power companies, that the Nissan Corporation could share power with the grid through a language, and then the car could charge the grid could charge the car. And it's a grand idea. And eventually you'll see that over here on our side of the world, we're going to something like that also. We know that General Motors and Ford are both working with Pacific Electric and Gas to come up with ways to hook up into the grid and work it. The reason I brought this up is because in order for us to pack all the energy into these batteries to use this CHAdeMO connector, or to use what we call a combined charging system, I'll show you a picture of that next, we're actually pushing DC voltage into that DC battery at a very large rate. We're pushing almost 400 volts into that battery pack. And while that does allow us to get 80% state of charge in about 20 minutes, it really degrades the battery. So the manufacturers have figured out level 2, that 220, 240 volt system, is the best way to allow you to charge that battery pack, taking 6 to 8 hours to do it, but it takes care of the cells as best as possible. So as we go forward, the new used car check is going to be do a battery report on the vehicle. And we've got manufacturers like Nissan right now will tell you how many times it's been quick charged and how many times it's been discharged below 30%. They actually keep track of everything. And if you work with a Nissan Leaf, you'll see in order to keep the warranty up, they have to have a battery report done and generated every year in order to keep it up. So it's just a different way to do things. The plug up on the top, what we call the electronic vehicle supplied equipment, ESVE, that is the charging plug. And you'll see that it can either go from a 110 or a level 1 charger, or we can simply go ahead and plug it into our dryer outlet, that 220 volt, and that would be a level 2 charger. Over on our side of the world, we've adopted what we call the J1772 spec. Now you'll notice we have 5 ports on this connector. 2 of the ports are actually the charging ports. And when we do that, that's where the electricity will go through to the charge system on the vehicle itself. The other 3 ports, 2 of them are for communication. As soon as you plug these chargers in, there's a communication that goes back and forth between the charger and the car to make sure that neither one will call for nor deliver more amperage than the other one can handle. So it's charger, hey, I'm a car, I'm going to give you 110 volts and I can do it at 16 amps. Is that okay? And the car would be like, yeah, I'm okay with that. And of course, it doesn't happen exactly that way, but it's a conversation that goes on with communication between the car to make sure that we don't overload it. The third pin down in the middle is what we call a proximity sensor. If that's not hooked up, the vehicle understands that that charger is not fully engaged and there's no way that we're ever going to allow any current to pass there. I bring this up is because when you get a vehicle that's not charging, you guys are going to have to understand how to diagnose this and look to see if they communicated, look to see if it understands proximity. And some of the things that I've been stung with before, if you work on, say, a Ford, a plug-in hybrid from Ford, one of their energy products, the module has to be plugged in to the circuit in order to actually read it with your scan tool. So all of this changes the way that we diagnose, and charging is one of those things that's going to fall to us, the technicians, to fix for the customer. So whether we use the 1772 connector or over on the right, where we see we've added the DC to DC quick charging to that same connector, that now becomes what we refer to as CCS. That is the standardized connector that we are going to use going forward for everybody except the folks over at Tesla. They're still using their own connector. However, about 2 days ago, Tesla said they were offering right now through Tesla a CCS to Tesla connector for $250 that will allow all Tesla owners to go ahead and use the public charging stations that are being implemented right now. So the connector, adapter, whatever you're going to call it, is going to allow us to go back and forth between the Tesla supercharger and the CCS for the people that have the Teslas in their driveway or in their fleet. Little chart that shows us the quick charging. This is from the folks over at Nissan. They're basically showing you, like your phone, if I go ahead and push a lot of current into it, I can get my state of charge up to about 80% in that first 20 minutes. But in order to do that, I have to step down the current that I'm pushing into that battery excrementally as soon as that battery starts to heat up. So I start out with high current to get the charge into the battery, and I have to start stepping it down, which means that last 20% of that fill is going to be just like your phone, right? We get to that first 80% in the first 5 minutes or 10 minutes you plug it in, and that last 20% takes forever because we've had to step down that amperage. If I use a normal level 2 charge and wait that 8.5 hours, you'll see that we pack a steady amount of current in it. Although it's not a high current, it allows us to build a very, very nice ramp up to that battery state of charge to a full 100%. The reason I bring this up is, again, it's a kinder way to treat the batteries. And most manufacturers have started leaning towards, listen, we understand that we want to get these things charged up fast, but you will have a longer battery life as long as we continue to use that level 2 charging. Battery construction over the years has changed. This is one of the first packs that I got to take apart. It was one of the packs that was bolted underneath of a vehicle. This isn't a true skateboard pack. This is actually bolted to the lower part of the chassis on a Nissan Leaf. In 2018, they redesigned these battery packs. So they do what they call a pouch cell. It's basically a very thick Mylar bag with the anode, the cathode, and the electrolyte built into it. So they're going to take 4 cells and build them in a block, 2 blocks per module, 8 cells per module. They give us 24 batteries or 24 modules in each one of these battery packs. And if you look, the design here was modular. So Nissan felt that if we ever had a battery problem, we would not have to replace the entire pack. This became a serviceable battery pack. In reality, most of these Nissan packs are still in the vehicle right now, and they've never really suffered from a lot of problems. However, it was a big step forward in battery technology, to the point where if we look at an Ultium cell from General Motors, it's a very similar looking cell to this. If we look at the cells that come out of your Mach-E, the Ford Mustang Mach-E, they're going to be very similar cells. We'll take a look at the round cells from Tesla coming up. I mentioned this a little bit earlier. This is a Ford Focus electric. In the background is a car that I owned, and in the foreground is a electric Focus. And you'll see there was nothing more than the electrification of an existing platform. And getting an opportunity to drive this car, I will tell you, that's not a turbocharged Focus in the background. It's a regular 2-liter. Pound for pound, dollar for dollar, drive for drive, you could not tell this was an electric car. It performed just the same. It stopped the same. It started the same. It just didn't make noise. It was an incredible experience for me to see how seamless that this could be. And then you realize that there was a lot of problems that they had to overcome because it was the electrification of an existing platform. If I look underneath the hood in this and just look at the cooling loops, just look at some of those hoses there, guys. And this is what I wanted to talk to you guys about opportunity. While we're not going to have the internal combustion engine opportunity for service work, there's a lot of cooling loops. There's a lot of regular service work that is going to be a big opportunity for everything that we see that has either hybrid or electric propulsion. The skateboard pack, the people that really made it popular and brought it on, of course, was Tesla with their Model S. So I remember the first time I saw one, I'm like, well, what are you going to do? Just glue a car to the top of it? And the response was like, well, yeah. And then the more I thought about it, I go, that's absolutely brilliant, right? So we make the chassis, we put all the weight low, we make all the components of the car, make their form, fit, and function serve the purpose of the car. So when they started using these 18650 cells, which were basically those little green cells up in the top corner that you see in everybody's rechargeable flashlight. They bought cells off the shelf for everybody else to use. So these things had 444 cells in each module. And by the time we added them all up, there were over 7,000 batteries in the bottom of this vehicle. And they were all coated with this intumescent coating that basically, if we had a thermal runaway on one of these cells, it would protect all the other cells from having the same thermal runaway or seeing any of that heat and affecting them. So the innovations that were done here, from the point that we took a hydraulic tube, a tube full of glycol, and glued the batteries to it machine gun belt style or bandolier style, and then assembled these battery packs, was just so innovative. Well, he continued to work forward to make energy density in these cells even better. And when they came out with the Model 3 and the Model Y, they started using 2170 cells. And what that means is 21 millimeters around, 70 millimeters in length. At the time of the introduction of them, this was the highest density cell in the world as far as energy went. So of course, they were able to decrease the amount of cells in each one of these battery packs, therefore getting rid a little bit of the weight. Now, the latest innovation, and we're not going to get here to service these, but you need to understand what happened here. The latest innovation, this 4680 battery, which was just announced that Porsche and Audi are going to start using round cells now also. This was a big innovation because they had 5 times the energy, 16% more range, and 6 times the power. And if you get past the marketing part of it, you realize, well, it's about 5 times the cell, the size of the other cell. That marketing kind of makes sense, right? It's 5 times the size, so it has 5 times the energy. But what was really neat is these were made what we called tablets. In order to make a battery, up until now, we basically took 1 sheet for an anode and 1 sheet for a cathode, welded a tab on each end of it, and coiled it up like a jelly roll. Well, we have a situation where there's an electron on one end of those sheets that has to go the whole way through the jelly roll to the tab to get out to actually get to where it's going to do its work. If you look in the bottom right-hand corner, what this tabless design is, and instead of welding a tab on it, they just snipped the end of it. And as they rolled the battery up, they crimped the ends over, making so that every battery, every electron only had about an 80 millimeter run for any electron to go to. And it increased the efficiency of the cell by decreasing the amount of resistance in it. And what that means to us is that it's just a more efficient battery pack. We need to understand, when this became a structural battery pack, it is not serviceable by us in the aftermarket anymore. If you guys look into some of the information that's coming out right now trying to get these apart, you will destroy the pack trying to get to the cell level. So fixing cells is not going to happen. What I take away from this is we are honestly watching the evolution of the battery and the technology, and it happened in real time. Some other innovations that everybody has copied is taking the motor and the inverter and moving it low in the chassis. So you'll see that while we have a 3-phase motor as well as an inverter, we do not take up time in the frunk or the trunk of the vehicle or any space up there. We put this low into the chassis, as low as possible. The inverter is what we're going to use to synthesize the AC electricity to drive that motor to make the vehicle actually run. In between them, we're going to sandwich our transaxle or our transmission, whichever way you want to see it. This has changed a little bit. If you look at this design, it was an absolute great design. We could put a motor on one side, transaxle transmission in the middle. We would have a gear reduction in there, and we could put the power inverter on the other side. When we went to the Model 3 and the Model Y, we took the inverter and actually mounted it to the front of the transaxle, which was more efficient because we could dissipate heat a lot easier that way. Well, when that happened, we adopted that same style and we actually were able to put two motors on the back of your Plaid. And that's what takes the place of the inverter back there. So the folks over at Tesla, by taking all of these heavy assemblies and moving them low into the chassis, actually were able to improve the performance of their cars and integrate a lot of the electronics into one location, and therefore getting rid of a lot of the cabling and a lot of the problems that we had associated with that as the cars were built. Now, when it comes to a three-phase motor, remember when Tesla invented this motor, the real Tesla, way back in the day, it was one of the biggest inventions or innovations that we've seen in modern history. And to this day, I'd really challenge anybody to come up with anything that's a bigger mover for the Industrial Revolution and just our world today than the inductive motor. I mean, it changed the world. What this means is we now have instant torque. I have 100% torque available at 0 RPM. So what it means to us is no matter how much technology I try to bolt on an internal combustion engine with turbochargers and variable valve timing, I will never get to the efficiency of this electric motor, nor will I match the torque curve because it's going to be 100% available. So the efficiency of the electric motors is one big push as to why we're going there. In order to synthesize that AC electricity from that DC battery, there's a big inverter built into there, and it uses what we call insulated gate bipolar transistors to take and synthesize an AC sine wave to get the motor to move. Now, remember, these are synchronous motors, and what that means, it will run at the RPMs of the switches that we make the motor move at. And if you think about your housing electricity, we're at 60 hertz, right? Everybody knows our AC electricity in our house is at 60 hertz or 60 cycles per second. So every motor that we plug into the wall will automatically run up to 60 cycles per second. That will be the speed of that motor. So what we do in order to control it, to give us throttle, we control the speed of those cycles. And we take the insulated gate bipolar transistors and we actually make the hertz from slow to high. So we apply the energy to the electric motor to get it to take off slow and then eventually drive at higher RPMs. That's the control takeoff. And this is the device that actually controls that. What's important to understand here, our serviceability is going to be for cooling here. These have to be cooled. So it's important for us. You can see the hose down in the bottom corner, that this is our opportunity on electric vehicles for coolant service, for leaks, for just the things that we're going to have to service on them. As we go forward in the future, innovation is happening all the time. This is General Motors' Ultium platform. The idea for General Motors is we're going to build a skateboard platform, and we're also going to integrate that with modular motors and modular battery packs, meaning that I can build this with 4 battery packs, 4 battery modules, 8 battery modules, 16 battery modules, and we'll be able to take this same chassis and we'll be able to move it from large vehicles to small vehicles just by changing the amount of battery modules that we put into it. Some other things that General Motors did that were very interesting, they've equipped every one of these to be either front wheel drive, 4-wheel drive, or rear wheel drive, depending on where they want to put the modular motor on these chassis. So you'll be able to get a rear wheel drive Blazer when it comes out in 2024. You'll be able to get an all-wheel drive Blazer, and you'll be able to order a front wheel drive Blazer based on your needs and the packaging you want in that vehicle. Now, we've all heard of how cool electric cars can be, and everybody's heard of Tesla's ludicrous mode. Well, General Motors has not stayed still on this. If you look into the new Hummer HEV, that vehicle has what we call a WTF mode. And it's actually watts to freedom, so don't get all excited there. What it does is they very dramatically start about a 20-second countdown on the dashboard for you. And what they're doing is super cooling the battery, the inverter, and the motor. Because when that countdown gets to 0 and that space music in the back of your mind that they're playing through the speakers finally quits, it's going to tell you to launch the vehicle, and you'll be able to unleash 1,000 horsepower at the end of your foot and take a 9,000-pound behemoth to 60 miles an hour in under 4 seconds. WTF? So when I think about electric cars, I don't want to continually think about my Nissan Leaf and my Toyota Prius. There is some serious horsepower and torque available at these electric motors, and now the manufacturers are starting to use it. If I look over here at the flagship from Ford, their electric vehicle really got real to me when the manufacturer decided they would take the best-selling vehicle in America for the last 45 years and decided to make an electric pickup truck. Not only did they do it right with the electric part of it, but they also made sure it was available in all trim levels, meaning that you can get an entry-level work pickup truck and theoretically get into one of these for less than $50,000, which isn't far from a regular four-wheel drive pickup truck from the same manufacturer. Ford Pro and the Ford Motor Company has gone all in and are fully supporting the switch to EV, not only on the F-150, but some of the other players. The newest offerings from Ford, we have the best-selling delivery van in the world right now as far as electric goes. That's going to be your Mach-E, your E-Transit, and of course the Mach-E, there's a waiting list to get these. So the electrification from Ford has become real. I don't know if you're aware of it. Every once in a while, we do see innovations come out. Ford took a super van over to Goodwood this year and actually took a 2,000 horsepower super van that they had built all electric on one of these chassis and took it over. It was quite impressive what was over there. For a long time, the ability to get data out of our scan tool has been there, and a lot of people miss this opportunity. This is very early, like a 2002 Prius. And what we're looking at is all the battery voltage displayed on my scan tool. And one of the tests I would have you guys do to look for a battery pack that's not balanced is actually pull these up and put the car in reverse and monitor these voltage while you're trying to move the car. You'll see if I have a subject cell like we do here, while everybody's at 16 volts, battery pack number 5 has dropped down to 15. And all we did was basically back the car up a little bit. So we can see with our scan data how we're starting to already be able to diagnose the high voltage systems and make sure that we're aware of what's going on with the system. So this has been around for a good long time. If we do get to the event where we have to work on some of our high voltage systems, there are special tools, as I said before, that we need. This is a high voltage insulation tester. This is a meter that comes from our friends over at Bosch. And what's different about it is it has the ability to send out 100, 500, or 1,000 volts through its leads. And we're able to use this to see if that high voltage would leak out of my high voltage system. Over on the left-hand side where it says good circuit, you can see up in the top corner, I pushed a button and sent 500 volts out through the system. And my meter's telling me I have over 1 million ohms resistance and I still have 500 volts inside of that wire. So if I was testing a high voltage system, it's telling me that none of the voltage had leaked out to where we could sense it on the chassis. On the right-hand side, I had that same 500 volts, but it leaked right over to the chassis, and my meter is telling me there's no residual voltage over here, and there is zero resistance between the high voltage system and the chassis ground that you have me attached to. So besides having gloves, one of these hybrid insulation testers being able to tell you the amount of voltage remaining on the system and how many ohms there were to dropping that resistance is going to be how we as a technician are going to check for high voltage leaks. Now, we're about 10 minutes after. Are we still okay, Brenda? Would you like me to continue going on? Is everybody okay to run a little bit longer?
Yeah, it's like you got a
Yeah.
car with a baby.
Yeah, I'm gonna leave it up to our audience. What do you guys think?
I'm okay.
I got a couple more to go through. We're getting towards it. I just want to cover some insulation testing at the end. So I'll just roll through and make sure that we give you guys the maximum that we can. So the last thing I'm going to go through is an insulation test on a Prius. This is a very early one. And as I said, this is probably what you're going to run into first. So this vehicle came in and it was setting one of those isolation faults. And the chart that you see in front of you is basically what I use to guide myself to understand how these systems power up. And what we're telling you is if you get an isolation fault, we want you to go back and clear the codes. But instead of starting the vehicle up, I want you to go ahead and wake the vehicle up in stages. First thing I want you to do is get the vehicle ready with the key on, but not the ready light. So all I want you to wake up is the battery pack. Then I want you to clear the code and see if that isolation fault comes back. If it does, we need to understand as technicians in this first step, the only thing that is awake is the battery pack and the module. Therefore, if it set that isolation fault right now, my isolation fault should be somewhere in that battery pack or module. If that code does not reset, the next thing I'm going to do is push the start button to put that car into ready mode to get the little green arrow or the green car to appear up on my dashboard. When I do that, I've now woken up the inverter and MG1 and MG2. And if the code resets, then I actually know who I just woke up in my high voltage system. If the code doesn't reset, then now I'm going to actually drop the vehicle in gear, which will energize MG1 and MG2 and make them actually put energy through them. If the code sets now, then I'm probably looking at the cable that leaves the inverter or the motor generators themselves inside of the transaxle. With that being said, the Prius that we have a problem with, we'll go ahead and set the isolation fault once we actually start the car, which means we have, that's step 2, that we have determined that we either have an inverter or MG1 or MG2 that is actually setting my isolation fault. In order to test this properly, and this is something that technicians have to get used to, there's disassembly that's needed on the car. On these early Priuses, you have to take the whole cover off. And in order to get back there and do testing properly, we found it best to remove the cowl and the wiper motor just so you can get to them and work so you can see it. We've done this on Windstars before. We've done this by removing wheel wells out of vehicles to get to, a good area to work with. So it should be nothing new to do a little bit more of the disassembly. As soon as we get the cover off, and of course, this is a Gen 2 because it has separate covers, we want to verify that we have low voltage as our high voltage contacts because we want to make sure that we're not working with high voltage at this point. As soon as the cover is removed, it's our job as a tech to make sure that we don't have high voltage here. And now in our meter, we're down under 10 millivolts. So obviously we've dissipated all the energy. My gloves can come off and I can go ahead and start to work unencumbered. Now we're going to take the cover off to go down to MG2. As soon as that cover's off, we've made sure that we have little energy left, little amount of voltage left. Now we're going to start doing our isolation testing from the chassis ground the whole way through every one of these wires. And you can see in this case, we're putting 500 volts onto the wire. It remained on that on the meter, that 555 that you see there, and it was over 17 gigaohms of resistance. So that is an isolated or insulated circuit, and that is a wonderful test. However, when we get to MG2, you can see we remove the cover, and when I test the windings, I get 11 gigaohms, and I'm retaining over 1,000 volts on the right-hand picture. So in this case, we're testing the battery cables going back to the battery to see if they have any high voltage leaks. Again, that's a negative test. That's not where our voltage leak is coming from. Now we go over to the right-hand picture, and with the gloves on, because we're going to go in there and test for high voltage, we're going to go ahead and take that cover off. And now when I back probe the isolation or insulation test going down to MG2, we'll see that it only has about 1 million ohms of resistance. Toyota's published spec is over 2.5 million ohms of resistance. So right now as a technician, I have found where my isolation fault is. However, we need to understand that we are still hooked up to the inverter and the transaxle at this time. So in order to understand if the short is in the inverter or if it's in the transaxle, I'm simply going to have to unbolt these cables and test them individually. Once I take these cables loose and test them individually, I find out that the 1 million ohms of resistance is actually occurring down inside of the transaxle. By doing this type of testing without removing the transaxle first, without having to take it apart, we understand that our isolation fault is occurring inside of the unit. Now, we would always take total mileage into the unit before we referred to a repair on it. And in this case, we'll probably end up replacing the entire transaxle. But what was found inside of this unit was nothing more than one of the windings was burned through. And remember, if you find one of these windings burned through because it's a Y winding on these motors, just like your alternators, all three of them are going to test bad. So it's just a way for us to test for isolation or insulation faults when it comes to our high voltage systems. Cooling your high voltage batteries. Remember, these batteries are just like you. They do not like temperatures below 65 degrees, and they do not like temperatures above 105 degrees. They're very uncomfortable at that point. So we spend an awful lot of time and energy making sure that they are cooled. We can do this with air. We can do it with liquid. And the modern ones, the latest ones, are actually doing it by implementing the refrigerant directly to the base of the battery pack, and that becomes the cooling of it. Opportunity for service for all of us are cabin air intake filters. Most of our early hybrid vehicles use cabin air to go ahead and cool those battery packs. We need to be cognizant of the air filter itself and also the air inlets. This is an old Honda. It was up on the package tray. We've seen Ford put them on the front of the back seat. So if somebody throws a blanket or a seat cover, they cover it up. We've seen other manufacturers move it over to what would be called the D pillar. And if we hang dry cleaning or laundry over there, that can also plug those vents up. So just make sure that airflow is important. Underneath of our Nissan Leaf, everybody has a bunch of covers that came off of a car laying behind their workbench somewhere. Turns out we got to start putting these things back on because especially on this Leaf, there is no battery cooling other than airflow. The little NACA ducts that we've circled there, the rear diffuser panel that you see, those are all part of the aerodynamics to make sure that the air flows across that battery and keeps it nice and cool. The things that happen to batteries when they start going ahead and overheating, they start to vent, it causes catastrophic failure. While this is a very, very early nickel metal hydride cell, the same thing would happen to anything with lithium if we decided to overheat it, and that's why it's so important. Remember that there are cooling fans involved in most of our earlier hybrid vehicles because of the airflow that we use to cool them. These are suspect to failure, just like any other blower motor out there. They are suspect to dog hair and debris that get plugged up in them. And you're going to test them the same way that you would test your normal blower motor. We would be able to put an amp clamp around it, look at the brush to commutator contact, as well as using bidirectional control to determine if it can go ahead and run it the way that it's supposed to be run. And if the feedback coming back through the PCM or the battery control module actually makes sense. There's a little better shot of how Tesla and most other manufacturers are actually interwinding a small strip of glycol in between the batteries. Remember, it never actually touches the batteries. What they've done is used the outside of the battery as a heat sink and allowing that water and glycol mixture to go ahead and pull the heat out of the batteries as it runs through that battery pack. This is a service opportunity for us, and I would advise everybody to start embracing 50-50 mix direct from the manufacturer of the antifreeze, not the manufacturer of the car, but start using a 50-50 mix because hard water and the chemicals that we see in our drinking water are really not going to play well with the electronics we're trying to cool. Just a live shot of that 2170 cell pack that Tesla had put together gives you a pretty good idea of how that bandolier goes through there and tries to make sure that we pull the heat off of those battery packs. Chevy Volt was a very popular car. This is an opportunity for me to tell you about all the different cooling loops that are on these vehicles. You'll see in this picture, there's 3D gas bottles, but there's actually 5 different cooling loops on this particular Chevy Volt. So understanding the service opportunity that we're going to have out there when these start coming in and the amount of redundant services. If you have 2 or 3 cooling systems, that means you need 2 or 3 services to go ahead and clean those out and make sure that we have the proper amount of antifreeze, the proper strength, and the proper acidity in there at all times. This was one of the first vehicles to come out that actually combined the air conditioning with this system to the point where we will use air conditioning to cool the coolant down, to send it down to the battery to cool it. We are getting what we call a chiller that utilizes the air conditioning system in the battery coolant loop to help once again control the temperatures inside of those batteries. The latest and greatest things that we're seeing from BMW, and looks like some other manufacturers are trying to apply for patents here, is we will stick an actual air conditioning manifold in the bottom of the battery pack and allow the air conditioning itself to cool the bottom of the cells. And by doing this, they've actually come up with a free lunch with physics, and it has to do with something called a heat pump. So in the very near future, General Motors is going to introduce it on their Ultium platform. They will use the heat that's introduced into the refrigerant in the battery and the electronics to create the pressure in the refrigerant. Then they'll use an electronic valve as the orifice tube to drop that pressure. And the more you think about it, the more it's like, well, this would be a self-feeding system, because the hotter that you got the engine, the hotter you got the motor, the inverter, and the electronics, the more pressure we would introduce into the refrigerant, the bigger pressure drop we could create, so the bigger temperature we could remove at the same time. So closing this loop of refrigerant and allowing the heat to create the pressure in the refrigerant and then using an orifice tube to drop it allows us to get more efficient. As we get we'll go forward, you'll see manufacturers had figured out, instead of using electricity to try to heat the battery, we can run a small current through the motor and allow the current itself to heat the battery. So every time I read an article, every time I look into a manufacturer theory and operation, there's another innovation that's going to help bring this on. So my parting thoughts would be that 2035 is going to sport a new automotive landscape for us, right? Energy storage, the solutions on battery tech, battery size, battery chemistry, they're going to continue to evolve at an incredible rate. Our powertrains are getting much tighter and much simpler. They're actually figuring out how to make them more and more efficient. So our opportunity for the internal combustion repairs are going to go away, and we're going to have to rely on the maintenance and the repairs that are going to present themselves on the systems that we will have at that time. Just like anything else you guys work on, we need to research and use all the materials that are available to us when we work on vehicles. And if we don't understand a new system, we have to ask or look it up. Be a diagnostic Einstein, plot your strategy, think, and before you go ahead and jump. And once again, plan your work, whether you're a technician or you're the shop owner or you're the one driving who you're going to bring into the shop, plan that ahead of time and then execute that plan. The best diagnostic tools are the ones that you can get the best job efficiency out of. So with that being said, that's it. I've had a pleasure telling you guys what I told you today, and I'd like to thank everybody for listening. So if we have any questions, if you want to moderate, I'll stick around for a while. Other than that, if you guys want to get back after our long lunch, I fully understand.
That was really awesome, Bill. I appreciate this.
Well, thank you.
Thank you.
Do you have this totally recorded? If I want to share this with text, this is some Napa training that we can tap into. This is awesome.